Welcome to our presentation on HDFS file block replication. Let's start with an overview of HDFS. HDFS, or Hadoop Distributed File System, is designed to store massive datasets reliably across clusters of commodity hardware. This means it uses standard, affordable servers to handle very large amounts of data. The core principles of HDFS include fault tolerance and scalability. Fault tolerance ensures that the system can automatically recover from hardware failures without data loss. Scalability allows HDFS to scale out to thousands of nodes in a cluster, handling petabytes of data. HDFS follows a master/slave architecture. The master node is called the NameNode. It manages the file system metadata, such as the directory tree and the mapping of files to blocks. The slave nodes are called DataNodes, which store the actual data blocks. This architecture allows for efficient management and distribution of data. Now let's discuss how HDFS handles files, blocks, and replication. First, file splitting. HDFS divides large files into fixed-size blocks. The default block size is 128 MB or 256 MB, depending on the version and configuration. For example, a 1 GB file would be split into 8 blocks of 128 MB each. This block-based storage allows HDFS to efficiently manage large files and distribute them across the cluster. Second, replication. Each block is replicated multiple times across different data nodes. The default replication factor is 3, meaning each block has 3 copies. This replication is crucial for ensuring data durability and availability. Even if 1 or 2 copies are lost due to node failures, the data remains accessible from the other replicas. Let's dive into the replication mechanism. When a client wants to write a file to HDFS, the process begins with the write request to the NameNode. The NameNode, which manages the file system namespace, grants permission for the write and provides the client with a list of 3 data nodes for each block. These data nodes are chosen based on the block placement policy, which we'll discuss later. After receiving the list, the client creates a pipeline for data transfer. The data is streamed in a pipeline fashion. The client sends the first block to the first data node DN1, which then forwards it to the second data node DN2, and DN2 forwards it to the third data node DN3. This pipeline approach minimizes latency and efficiently utilizes network bandwidth by overlapping data transfer with replication. Continuing with the replication mechanism, after the data is written, we have the acknowledgment flow. Once DN3 receives the block, it sends an acknowledgement back to DN2, which then sends an acknowledgement to DN1, and finally DN1 sends the acknowledgement back to the client. This reverse flow ensures that all data nodes in the pipeline have successfully stored the block. Meanwhile, the data nodes also report the block information to the NameNode. The NameNode then updates the metadata to record the locations of the block replicas. This metadata is critical because it allows the NameNode to know where each block is stored for future reads and for maintaining the replication factor. Now let's discuss the replication factor RF. The replication factor is the number of copies maintained for each block. It's configurable per file or per directory, meaning you can set different replication factors for different datasets based on their importance. The default replication factor is 3. However, there is a trade-off to consider. A higher replication factor, such as 4 or 5, provides better fault tolerance because there are more copies of the data. But this comes at the cost of higher storage overhead. For example, with RF equals 3, you use 3 times the storage of the original data. So, while increasing RF improves reliability, it also increases storage costs. Therefore, it's essential to choose an RF that balances your availability needs with your budget. Another key concept is block placement policy, which is based on rack awareness. This policy determines whether replicas of a block are placed to optimize both performance and fault tolerance. The strategy is as follows. 1. The first replica is placed on the same node as the client, if possible, or on a random node if the client is outside the cluster. 2. The second replica is placed on a different rack. This ensures that if an entire rack fails, we don't lose all replicas. 3. The third replica is placed on a different node in the same rack as the second replica. This minimizes inter-rack traffic because reads often come from the same rack, and it also provides a good balance between fault tolerance and network efficiency. By placing replicas across racks, HDFS minimizes the risk of data loss due to rack failures and reduces cross-rack bandwidth consumption, which is typically more constrained than intra-rack bandwidth. HDFS is designed to handle failures gracefully. Let's look at how it handles DataNode failures. The NameNode periodically receives heartbeats from each DataNode. If a DataNode fails and stops sending heartbeats, the NameNode detects this and marks the block stored on that node as under-replicated. This means those blocks now have fewer than the desired number of replicas. To address this, the NameNode triggers a re-replication process. It identifies which blocks are under-replicated and then instructs other DataNodes to create new replicas from the surviving copies. The re-replication follows the same rack-aware placement policy to ensure that the new replicas are placed in a fault-tolerant manner. This process restores the replication factor and ensures data durability. Sometimes, a cluster might end up with more replicas than required, a situation called over-replication. This can happen, for example, when a data node that was thought to be dead comes back online and brings its blocks back, or due to re-replication occurring in multiple places. HDFS handles over-replication by periodically checking the replication status of each block. If a block has more replicas than the specified replication factor, the NameNode will instruct some DataNodes to delete the extra copies. This routine cleanup ensures that storage is used efficiently without unnecessary overhead. The NameNode plays a central role in HDFS. It is responsible for metadata management, which includes tracking the locations of every block and the replication status of each block. The NameNode keeps this information in memory for fast access. Critical tasks performed by the NameNode include replication monitoring. The NameNode constantly monitors the replication status of all blocks. If it detects under-replicated or over-replicated blocks, it initiates actions to correct the situation. Rebalancer. The NameNode also runs a rebalancer process that ensures data is uniformly distributed across the cluster. This helps in avoiding hotspots and makes sure that no single data node is overloaded with data, thus optimizing performance and storage utilization. Replication in HDFS offers several key advantages. 1. Fault tolerance. By having multiple copies of data, HDFS can survive node failures or even entire rack failures without data loss. If one replica becomes unavailable, the system can automatically switch to another. 2. Data locality. HDFS enables data locality for compute tasks. When processing data with frameworks like MapReduce, tasks are scheduled to run on nodes where the data resides, or at least in the same rack. This minimizes network transfer and speeds up processing. 3. High availability. Multiple replicas allow for parallel reads. Multiple clients can read different replicas of the same block simultaneously, increasing read throughputs and reducing latency. Despite the advantages, replication comes with trade-offs and challenges. 1. Storage overhead. The primary trade-off is storage cost. With a replication factor of 3, you need 3 times the storage of the original data, which is a 200% overhead. This can become expensive for very large datasets. 2. Network traffic. Replication requires data to be transferred over the network. When writing data, the replication pipeline uses network bandwidth. Similarly, re-replication after failures also consumes bandwidth. In a busy cluster, this can become a bottleneck. 3. Tunable parameters. To optimize HDFS, administrators must tune several parameters. These include the replication factor RF, block size, and heartbeat interval. Choosing the right values depends on the specific workload, cluster size, and network infrastructure. For instance, a larger block size reduces metadata overhead, but might lead to inefficient storage for small files. The heartbeat interval affects how quickly the NameNode detects failures. Tuning these parameters requires careful consideration. This concludes the narration for each slide. The presentation covers the fundamentals of HDFS block replication, its mechanisms, advantages, and challenges.